So Galileo Galilei was an Italian mathematician, physicist, philosopher, and astronomer. And the experiment we are trying today was Galileo's experiment with measuring time using a pendulum. Now, Galileo's achievements include him proving that the planets revolve around the sun, which was contrary to the point of what the church believed, which was that the earth was the center of the universe and everything revolved around it. What he also proved was that the two masses of different weight, when dropped, they fall at the same rate and hit the ground at the same time, which is contrary to what people believed was that the one with the heavier weight and more mass would fall much faster than the one with the lighter weight. And through this, he changed the way people thought, and he changed science, in which science was believed to be proven logically, while now he changed that to be science is now proven experimentally, and science shall be proven through experiments and is only true through experiments. Now, what made Galileo use the pendulum to find time was one Sunday morning at church when Galileo was sitting and watching a chandelier on a windy day. He saw that no matter how hard the wind would hit the pendulum, he could see that using his heartbeat, he saw that as it went back and forth, the amount of time it took for it to cover one full period was the same amount of time. So, Galileo, through this experiment, started experimenting with pendulums to find a correlation between a pendulum's period and time, and he saw that time differs with the length of the pendulum.
When it was performed. This experiment was performed in the 17th century. Galileo knew he'd need more than just himself to perform this experiment. So he got 4 friends, and they waited till night. The way they used the experiment is they waited till a star aligned with a certain object, and as soon as it did, they released the pendulum. During this time, they realized that the pendulum would stop by itself. So what they had to do is they had to precisely push it, giving it just a little bit of energy to keep it going through this entire day. After a 24-hour period, they waited till the star realigned with the same object as the night before, and as soon as that happened, they stopped the measurements. They knew that one day consisted of 24 hours back then, so they divided the amount of times it swung by 24 hours and was able to get a more precise time and was able to find a constant, and which is what we use nowadays to find other experiments.
So how this experiment works and how we ran this experiment is we choose a pendulum and we change the length of the pendulum, because if we change the length of the pendulum, we can see that as it completes one period, it will take the exact same amount of time as long as the angles are small. But if we change the length of the period, change the length of the string, we see that the distance it covers, the amount of time it takes to go one full period is much shorter. And that we can set up the experiment to where we can measure time and find time. And through that, and back then, they didn't have time, or they didn't have a second to base everything off of. So what they had to do was they used water, and they let water fill up a cup or a bucket, and they measured the mass of that bucket, and they found that the amount of water in the bucket for different lengths would vary, but stay consistent. So what we did in this experiment was we ran this pendulum, and we started our measurements wherever the pendulum was at its maximum height. And the reason we did this is because it's easier for us to measure a point at which we are at maximum height rather than at random other points. So we let it run 10 times, and the reason we let it run 10 times, we measure 10 periods, is to lower the uncertainty due to human error, mainly human reaction time.
The way we measured this was through water. Now we figured that we could find the weight of how much water would flow during a period. So what we'd do is we'd measure this 10 times, and during that 10 times we'd let water flow. Once it reached the 10 times, we would stop this, put this on a weight, and then neglect the weight of the cup, and find the weight of the water. This would help us find and correlate L to T, which is what we were trying to find.
So in this experiment, we theorized that the longer the length of the string, the longer the period will be, and the more water will be inside the bucket. So if we have the length to this length, it will go back and forth as seen. But if we have it to a length, let's say, that is much longer and much more. But now, as you can see, the length for this one is much longer. And because it is much longer, that we'll see a longer period. And our theory, as we stated before, is that the longer the length of the string, the more water that will go in. So in our experiment, we used small angles. And the reason we use small angles is due to the small angle approximation. And this small angle approximation, what it tells us is that if you have a small angle, there will be little to no deviance in the height it goes back and forth through its period. This allows us to use an equation known as 2 pi times the square root of L over G, which is the length of the string divided by gravity, which the square root of L over G is 1 over omega. And 2 pi divided by omega is equal to the period time. What this also allows us to do is once we have the period, we can then divide the amount of water we get for each case or each experiment we run through to find the flow rate of the liquid. And if the flow rate of the liquid is consistent through all our cases, we know that we have an accurate time measurement. So this is our data collection that we have of the pendulum and the amount of water in the system. And as you can see, as the period or the length of the string was shorter, we saw there was an increase in the amount of water going in. And in the plot graph itself, it shows that the equation y equals 33.404x plus 26.402. That is the mx is the flow rate of the water going inside our cup, and the 26.402 is where we started, which is 0.1.
And the r squared is the uncertainty in the equation, so we are a variation of about 6% in this line. So we're pretty accurate from the graph. So right now, these are the points that we have. We started with 0.1 meters and moved all the way up to 1.3 meters. And this is for 10 swings. So we let the ball swing 10 times and then we stopped it. And then up here is 5 swings. So we did the same thing, 1.3 meters, went down. We don't have as many points for that one because we figured we'd have more accurate data in the longer swings. So we just went with a few in that, and then as you can see, this is another form of the graph. Instead of being in just a point graph, we have bar graph just to make it a little bit easier to see. And yeah, as you can see, the more time that went by, the more water that went up. It was kind of, we have like a few varying spots, like right here, it's a little hiccup or something. I guess we just didn't do too good a job that time. But every other time it's kind of it's somewhat linear from like here. Then we get that, and then it's a little bit steep here, but everything else is good. So that's how we got our data, and yeah. Okay, this is the uncertainty part, and what we'll be doing is talking about why our numbers just might be off by a little bit, or why they might not be, it might not be a constant that we get. So the first thing that we came up with is this right here. The lever in the water thing is obviously going to have some delay from my hand starting and stopping it. So that will give us a few seconds at most likely milliseconds off by the time. And then another variation we might have is from the pendulum. So obviously when I start the pendulum, it's going to swing back and forth. So one variation we're going to get is starting and stopping it. So whenever it's here, I'm going to start it, and then whenever it gets back, I'm going to stop it again. So obviously my reaction time is not going to be 100%, and I'm not going to get it exactly where it started. So I'm going to have some variation in that.
In conclusion, in this experiment, it shows that the period of this pendulum is affected by the length of the string, and the correlation between L and T are directly proportional.